Now this will be useful. I'll just come back to it. Okay, and let us just basically go back to our original discussion. Okay, what happens for ideal solution? But now today we'll be talking about ideal solution where the number of components, okay, or number of basically volatile components are 2. Okay, at least 2. Now, what I'm trying to say here is that, like, already we know that for any component, okay, I can write the same equation, okay, mu star plus RT over x. But say if I just call as 1 and 2, I'm just writing it like this. Okay. Now, in the early cases, where we are at the very first class on this chapter, on this topic, okay. Remember, we were saying that the ideal thing means actually if I vary the x1, let's say 1 is the solvent, okay. So if x1 is 0, okay, there is no vapor pressure basically, okay, and then the pressure actually varies like this. That was the ideal behavior, okay. But it is starting from 0, okay. Now think if I have now 2 components, 1 and 2, but 2 is also volatile, okay. So when x1 is 0, x2 is basically maximum, right? But in that case, the pressure will not start from 0 exactly. It will start from something because that will be the vapor pressure of 2. Okay, as simple as that. Okay. But each of them, okay, if they behave ideally, I'm assuming that the both are basically following Raoult's law, which basically tells that the pressure, okay, will be proportional to the mole fraction. Okay. And this is this. Okay. Alright. So we'll just start with that. Okay. So let me actually drop the 0 notation and let's write the star notation. So what I'm saying for component 1, okay. So I'll have basically x1, p1 star. Again, the p1 is basically the vapor pressure of pure 1. Okay. And for component 2, I have similar thing. Now, the question is when you are plotting now, okay. So I have to plot, I'll do a measurement. How do we do the measurement? We already discussed, right? So I have something like this, okay. Remember our very first picture, I had 1 and 2 here. In the earlier case, there was only 1 in the vapor. Now actually I have 1 and 2 together, okay. And all I'm measuring, okay, is the total pressure here with some pressure gauge. Okay, I'm just looking at what is the difference. That difference will tell me the pressure. Okay. Now that pressure is coming now, the total pressure. So I have to actually relate somehow, not P1 star, P2 star, I have to relate total thing. Okay, total pressure. Because what I will plot as a function of mole fraction of 1 or 2, the total pressure. Okay, which is contributed by both partial pressure of 1 as well as partial pressure of 2. That's as simple as that. Okay. And these are the only 2 equations. Okay. So let us just so this part actually has like mathematically very simple, but there are some conceptual things. So we will just discuss accordingly. Okay. Now okay. So that I can actually write it. X2 means actually 1 minus x1. Okay. P2 star. Okay. And then what will be the total pressure? Total pressure is basically addition of the vapor pressures. Okay. So I can just straightforward write it. It is basically x1 p1 star plus 1 minus x1 p2 star. Okay. Clear? Okay. You can just rearrange it like you can write it as p2 star. And then what I'll have, I can take x1 common. Sorry, I can take x1 common and then I'll have p1 star minus p2 star. Right? Fine. So I have a relation of p with x1. I could have written it in terms of x2 also. Okay. So now how the plot will look like? Suppose I am varying x1, okay, from 0 to 1. Okay. When x1 is equal to 0, which means it is pure x2 and pure component 2. Okay. So I'll have basically p2 star, right? So here actually I'll have non-zero. That's what I was telling you. Okay, that will be the vapor pressure of the component 2. Earlier it was not there because component 2 was non-volatile. Okay. So I'll start from somewhere, which is say here, which is P2 star. Okay. When x1 is equal to 1, I'll have basically the P2 stars will cancel. I'll have the pure vapor pressure. Okay. So I'll have something like this, P1 star. Okay. So this will be my ideal behavior. Okay. Now this, what we have just drawn. Basically here, x-axis is mole fraction of some component. Y-axis is the total pressure which I am measuring. Okay. Now think about it. What we have drawn here. Okay. This is x1. Okay. Now what was x1? Think about it. x1 was the mole fraction. Okay. In which phase? In solution phase, right? Like we drew a picture, right? Solution is equilibrium with the vapor. But remember that we started at the very beginning. Okay, that is the mole fraction in the solution. So when I actually measure this thing, this is kind of a behavior how the liquid mole fraction. Okay, if I change the mole fraction of the liquid phase, okay, how the total pressure is changing. Okay, so this is a behavior, ideal behavior, of course, okay, for a liquid. Now we could, instead of x1, I could have actually plotted the partial pressure of the component 1 or component 2 and looked at the entire thing. Okay, again, long story short, what I am saying is that what I am measuring basically the pressure. Okay, that pressure is contributed by both P1 and P2. Clear? Okay, but what is my variable? My variable is either x1 or x2. But what is x1 and x2? x1 and x2 are mole fractions of 1 or 2 in the solution. Because now coming back to your question, it is in that phase, liquid phase. Okay. So basically this describes how the behavior of the solution basically. Okay. Like this ideal thing, okay, is or it's a characteristic of the liquid phase, meaning how x1 is varying, how the total pressure is changing. But can I actually just derive an equation, okay, of P, the total pressure, versus the partial pressures of x1 and 1? Then actually I can connect it how the vapor mole fractions are changing. Because vapor mole fraction need not be same. Okay, it will depend, right? What are the relation, like what will be the mole fraction of their, right? So it will depend. So it will not be exactly equal because your P1 star and P2 star are not equal, right? Pure solvents vapor pressure for 1 and 2 are very different. So which means, like for example, one solution or one liquid, suppose water, is more volatile than the other liquid. Okay, so then of course the mole fractions will change in the vapor phase. What I just showed you is what is the mole fraction in the liquid phase. Okay, but how do I get the mole fraction in the vapor phase? The best thing is that you just connect it to the partial pressure. Because partial pressure is nothing but the total pressure into mole fraction. Clear? Okay. So what I am going to do is the same plot, but with a different variable. Okay. That is basically looking at the problem from the vapor's perspective. Okay. Now how do I do it? It's again very easy. Okay, I'm just using this particular notation. Okay. So I'm just writing it as say P1. Sorry, y1 star. Sorry, notation also here. Just one thing. P1 is basically the total pressure. Okay. So this is partial pressure. Now partial pressure means the pressure divided by the total pressure, right? Of 1. So if I just do it, what is P1? Okay. Now let us look at here. It is basically x1 P1 star. Okay. And what is P? This is the entire thing. Okay. So let us just write it. So what I have is x1 P1 star divided by, I have P2 star plus P1 star minus P2 star into x2. Right? Sorry, it will be so. Now look at it. Basically, I want an equation of this guy P, okay, with this guy. I mean y1. Okay. So what I want actually, instead of writing it in terms of say x1, okay, I just want to replace x1. Okay. What I want is that I'll write actually the total pressure versus y1. This is actually a curve. Okay. It is for P versus x1. I want P versus y1. All I have to do is to write this x1 in terms of y1 and find the relation. Okay. If I write y1 as this, what will be the x1? You can easily rearrange it. Okay. And if you do it, finally you will get something like x1 is nothing but y1 into star. Okay. So like this term. Okay. y1 p2 star. And then you should have p1 star. Okay. Plus p2 star minus p1 star. And look at the symmetry of these two equations. It is basically the similar way. Okay. So it's just you just multiply it and then rearrange all the x1 terms. Okay, and then do it. But then there will be a negative sign here. So that is being included here. Instead of p1 star minus p2 star, it becomes p2 star minus p1 star. Okay. You could solve it for y2 also. Okay. So that is x1. Okay. In terms of y1. So what will be the total pressure? So what I will do is that I will just replace here. Okay. Instead of x1, I will just write it in terms of that, so that I will get rid of all the x1. It's basically just playing with this thing. Okay. It's a very easy thing. Like what I did up to here is very easy. Okay. And all I am doing is basically writing in terms of partial pressure. That's it. Because I want to actually cast the problem in the Weber phase. Okay. How, if I basically look at the total pressure, how the partial pressures are changing, or the mole fractions in the Weber phase are changing. Okay. So the P, how will I get the P? Which is basically P2 star plus P1 star minus P2 star into x1. x1 is this thing. Okay. So if you do this thing, it will come as something like P is P1 star P2 star divided by P1 star so this is the same denominator. You can easily check it, right? So what I have is P2 star, okay, P1 minus P2 star into x1. Okay, x1 is basically entire things. Okay, so what I have, as you can see, in the numerator I have y P2 star, right? So here actually I have y P2 star. Okay, so that way you proceed, you get it. Okay. Now what I did is that, see here I have basically an equation which is P with x1, and now I have a P with y1. As simple as that. Okay, clear. Now I will just plot the same thing. Okay, but instead of x1, I'll have the variable as y1, which is basically the partial pressure of component. Okay. Now I'll plot this. But these equations are again identical or equivalent equation. Okay. These are equivalent equation, not exactly identical equation, because that is the equation which is telling how the pressure is varying with y1. Okay, partial pressure. Now let us just have a look. Okay, how that plot will look like. This is okay, right? And basically again I am repeating. So what I did is I did the pressure versus x1 for the two component system, where the both components are volatile. Okay, and then I said I will not actually use x1. Okay, instead I will just use a new variable which is the partial pressure, which is the ratio of the pressures. Okay, and since I have a P1 which is already solved in terms of x1 and I have total pressure also in terms of x1. Okay, I wrote it, but I just extracted the x1. Okay, wrote it in terms of y1, and put it back in the total pressure equation. Okay, now I got an equation for P versus Y1. As simple as that. Okay. Now again, just look at it. Look at the equation and let us see what is there. Okay, so I am plotting basically P, the total pressure, which I am measuring. Okay, but now as Y1. Okay. Now what could be the partial pressure range? Now partial pressure, again, it can be from 0 to 1 only. Okay. Think about it. When the mole fraction is basically of 1 is 0, its only 2 is present. So its partial pressure is also 0. When the mole fraction is 1, the partial pressure is nothing but the total pressure. Okay. So that range is also 0 to 1. Fine. Okay. When Y1 is 0, I'll have P1 star, P2 star by P1 star. So I'll have basically P2 star. Okay. So I'll have the same thing here. P2 star. Okay. When I have basically Y1 equal to 1, okay, this P1 star will cancel. I have P2 star, P2 star will cancel. I have P1 star. Okay. So I have the same thing. However, the equation is not linear. That time I had what? Something y equal to mx plus c. Okay. Now I have actually y equal to a divided by b plus c, x, something like that. Okay. Now the equation is nonlinear. So it won't be a straight line. Okay. What it will be? It will look like something like this. Okay. But it will depend in the sense like whether the curve will be like this or like that. That will depend on the relative partial pressures. Okay. Now, long story short, it is not linear. Okay. Now we have a conceptual problem. Okay. What we did? Actually, we have just varying component. Okay. And I am looking at the total pressure. Okay. Now, this is basically total pressure, how it varies with the component or the mole fraction. Okay. In the solution. Versus how the partial pressure, if I plot, okay, how it basically describes the total pressure. We see these are two very different things. Okay, and just like it describes the liquid variation, okay, this thing describes basically your vapor or the gas phase variation. Okay, so again, what I am saying here, right now, in the earlier case, actually I was writing only x1. Why? Because remember that 2 was not present in vapor. Okay, only in the solution phase I have the two things present. Okay, so the mole fraction has a meaning only in solution phase. But now I have something in the vapor phase also. Both 1 and 2 are present. So I could have actually looked at the vapor itself. Because everything is in equilibrium. Right? But if I look at the vapor phase, best quantity to look at is the partial pressure. Because it is directly connected to the mole fraction in the vapor phase. Okay. But now what I showed is that if I had plotted it versus y1, the same quantity. Okay. I have a nonlinear thing. Which means if I just plot them together, okay, how the total pressure is varying as a function as I am actually increasing 1. If I increase 1, of course the mole fraction x1 will also increase, also the partial pressure will also increase. Okay. Now, together, of course, as you can see, okay. So what I am saying here is basically say number of 1 or something like that. Okay. Which can be x1, which can be y1, whatever. Okay. The range is the same, 0 to 1. But I see that, and also the limits are also same, has to be. Because see, the total pressure cannot change when like things are changing. So I have P1 star here, I have P2 star here. And I see for x1 variation, it is very much linear like this. And for y1 variation, I have something like that. Okay. And then, think about it. I said that this curve corresponds to some perspective from the liquid and this curve corresponds to some perspective from the vapor. Okay. Now think about it. Okay. Now here is the most important thing. Okay. If the total pressure, okay, increases, okay. If I increase the total pressure, of course, I mean like more and more liquid will form. It makes sense because if I increase the total pressure, okay, which means actually there will be a more propensity of things going into the condensation, right? I mean, it's basically go to the condensation, right? So basically here, this line, okay, is telling me somehow, okay, how the system will behave, okay, in basically the, okay, think about it in a different way, slightly different way. If I actually reduce the pressure, okay, what will happen? So if I reduce the pressure, okay, I know that actually the vapor phase is more stable. Okay, liquid is actually stable at a higher pressure region. Okay. By the way, all these things, okay, forgot to tell you, these are all at constant temperature. I'm not doing any temperature variation. Okay, and I'm looking at the total pressure. I'm only doing composition variation. Okay. Now this, basically this region, if you just ask, okay, what is the most stable thing? This is liquid. It's the high pressure region of the liquid. Okay. So if I actually reduce the total pressure, okay, I see that at some point, okay, my variation, okay, in the total pressure which I am measuring, okay, is basically showing a Raoult's law like behavior, ideal behavior, okay, which is characteristic of the liquid variable, which is x1. On the other hand, if I actually start from a very low pressure region, okay, where actually the vapor was more stable, okay, if I just look at it from the vapor perspective, okay, so then I'll see that at a very high pressure limit, okay, when basically just the vapor is forming the liquid, something like that, okay, I have a curve like this. So what I'm trying to say here is that, physically try to think about it, right? I have basically an interface, right? I have a liquid, I have a vapor, okay, and I'm looking at the total pressure, okay. If I had actually huge pressure, okay, I'd expect that both the systems are existing as actually one phase, which is the liquid phase. Okay, that will be one extreme. Okay, and the liquid phase, how it, and suppose some vapor is there, okay, meaning I am having a situation where I have more of the liquid and little vapor, okay, that will vary like that. It's a straight line. However, if I actually think in the other way, okay, I started from a very, very low pressure regime, okay, where actually I had a little bit liquid, but most of it was in vapor, okay. I see the variation will be something like this, okay, which means this region, okay, is somehow telling me, okay, when the liquid and the vapor kind of coexist, okay. Now, when the liquid and the vapor coexist, which means actually there is a phase transition is happening, okay, for a particular temperature. So you can think, so suppose this is the total pressure, okay, suppose some pressure, whatever. Okay, so the total pressure, if I take a horizontal line, then the pressure is fixed. Okay. Now I see here, if I have a total pressure like this, I could have described the system from the liquid's perspective, that this was the corresponding mole fraction, or I could have actually described the system from the vapor's perspective, that this was corresponding to the partial pressure. Okay. Now this is an interesting situation. Okay, so if I have actually two components, okay, and then basically I'm looking at the thermodynamics of that two components, okay, I'm looking at the total pressure, but actually both components exist in both phases, okay, then I see that in the liquid phase, okay, the proper quantity or the correct quantity is basically the mole fraction, okay, but in the vapor phase, when I'm looking at the partial pressure, I see a very different behavior. Okay, it can be in the other way also. Okay, that depends. Okay, but it's certainly not a linear thing. Okay.